Thank you. So welcome Marcelo Hernandes to talk on value set of fractional ideals and the analytic classification of plane curves.
Thank you. I'd like to thank the organizer, Alexei, Alicia, and Veronica, for this opportunity to talk about this joint work with Maria Helenice Rodrigues Hernandes. And I hope that in the next edition of the MCA, I can meet you in person. The aim of this talk is present a solution for the analytic classification problem for the plane curves using algebraic algebraic aspect following the percussive idea of the Oscar Zariski. And in this talk, we denote by CF a germ of a singular plane curve given by the zero locus of a reduced element in the maximal ideal of the analytic power series ring. If Fi is a irreducible factor of F, we will denote by Ci the branch, the irreducible curve, the branch defined by Fi. So we are interested mainly in two equivalence relation, the topological and the analytical ones. And we say the curve given by F is topological equivalent to the curve given by G if only if there exists a homeomorphism from C2 to C2 such that the image of the neighborhood V of the curve CF is precisely the neighborhood U intersection to the curve CG. So this is the topological equivalence as consider the curve as an immersed germ in C2. When the homeomorphism phi is an analytic isomorphism, then we say the curve given by F is analytic equivalent to the curve given by IG. So consider a branch, a reducible component of F and the curve associate. We can, using, for instance, the Puiseux theorem present by Fessanta and by Sebastian, and we can consider a parameterization of it. And if Ci has multiplicity Ni, and this means the power series Fi belong to the maximal ideal to the maximal ideal to the Ni, but doesn't belong to the maximal ideal to the Ni plus 1, then we can parameterize the curve given by Fi by a pair of a power series and one variable such that Ai or Bi are non-zero. And in what follows, we identify the parameterization as a smooth map germ from C to C2 in the natural way. If we have a curve with R reducible component, we denote by the mu germ associated to this curve by a matrix where in each column we consider a parameterization associated to the corresponding irreducible branch. So the idea is consider the mu germ and analyze to the topological and the analytical equivalence. So about the topological equivalent, we have several results. For instance, if we have a parameterization of a branch Ci, we can identify the local ring OI. The local ring is the quotient ring by the ideal generated by Fi as a subalgebra of CT. And CT is precisely the integral closure of the local ring OI in its field of fraction. So we can consider the natural normalized valuation given by nu I, and the valuation is precisely consider the order or the multiplicity of the elements in CT, and we can collect the orders. So here we have the well-known convention. The nu of 0 is infinite, and we set the set gamma. And the set gamma is the set of all values, considering the respective valuation associated to each branch when we consider a power series H in the ZXY. This set has a additive semigroup structure, and the all finite part of the gamma, we denote by S, is precisely the classical semigroup associated to the curve, to the mu germ. And this semigroup has been considered by Garcia, Bayer, Valdi, Delgado, and this semigroup is a complete topological invariant. In the following sense, if we have two curves, we have R branches, then two curves are topological equivalent if only if their semigroup are the same. And the semigroup S and the semigroup gamma are mutually determinant. But gamma is not a finitely generated semigroup. But consider the tropical operation, the infimum in the sum, then the set gamma is a finite generate semi-ring. This structure, the tropical operation in gamma, has been considered, for instance, in some works of Félix Delgado and the Ethan Contrill and Renato Vidal also. So, and in this paper, we have a method to prove, to obtain the finite system of generator for the gamma, for this semi-ring. Okay, but what about the analytic equivalence? Because here we have a complete topological invariant. Consider the analytic equivalence. We can translate the analytical equivalence in terms of group action. And the group action, we can translate the analytic equivalence of mu germ is the symmetric group on R element cross the classical A group of the right and left equivalence in the singularity theorem. And the A group is the group of R diffeomorphism of C and one diffeomorphism of C2. And the action of this group on the mu germ associated to the plane curve is given in the following way. The A group, the action of the A group on a mu germ, a set of parameterization of a curve with R branches, is given by the composition of the respective parameterization with the inverse of diffeomorphism of C, and we consider the same diffeomorphism of C2 for each column. This is the A action on a mu germ in P. And the S cross A action is given in a natural way, is just to permutate the column of the mu germ. So we can translate in this way the analytic equivalence. And the idea is consider a mu germ and put in a special form and split the analysis. Put the mu germ in a special form, and we forgot for a moment the symmetric group, and consider the A action on the mu germ put in this specific form. So we split the group A in two parts. One of them does not introduce or remove terms in the parameterization, and the other part is important because allows to identify such terms we can remove in order to obtain normal form to perform the analytic equivalence. This is the general idea. So what is the special form we consider? Using a permutation, an element in the symmetric group on R elements, and the A group, we can permutate the branch in the mu germ in the following way. We group in each block the same branch according to the tangent line. So in the block B1, we put irreducible components, parameterization, branches that share the same tangent line. And the B2, we put another block with a common tangent line, and so on. So we can, using an element in the symmetric group, permutate the elements in each group in order consider the multiplicity of the branches. And we can order the blocks according to the minimal multiplicity of a branch belong to it. Okay, so in the block B1 we have a lot of branch that have the same tangent, and the second block we group parameterizations branch that has the same tangent and so on. We order according to the multiplicity inside each branch. We order the blocks according to the minimal multiplicity to the branches, and to finish this presentation, this block form, using the element in the A group that corresponding to the Möbius transformation, we can move the tangent line in the first block to the line y equal to 0. If you have in a second block, we can change the tangent line to the line x equal to 0. If you have an extra block, a third block, we can move the tangent line in order to consider the tangent line y equal to x. So this is the block form. So in that follow, we fixed a mu germ in the block form, and now we will consider the A action on mu germ given by this way. Okay, so in order to maintain the block form, we analyze which subgroup of A do this situation. And we consider the following subgroup of A. The A1, and the A1 is precisely the elements in A, in the group A, so that the first jet coincide with the identity. A1 tilde is very similar, but here we allow an extra term in the first jet of sigma, and we consider the homotety groups. And 8 is the homotety group, and is Ti times a non-zero constant, and sigma we have this one. And H prime is a subgroup of the H, where we consider alpha and delta equal. So considering this subgroup of A, we have the following lemma. In order to preserve a block form, the subgroup we have to consider is given by this table according to the number of blocks. If you have just one block, and this corresponds to we have just one tangent, so we have to consider only a composition of element N1, A1 tilde, and a homotity. We have just two blocks, two distant tangent. Elements to maintain the block form are given by a composition of elements in A1 and H, and you have three or more blocks. We have to consider composition of element in A1 and HI prime group. The group, the homotity group, doesn't introduce or remove terms, but the group A1 and A1 tilde, maybe we can remove parameters in order to obtain a simple representative element in the analytic class. So we will consider now the action of the group A1 or the A1 tilde, and we call G. G denote A1 or A1 tilde. If we have just one block, G is precisely A1 tilde. If we have two or more blocks, so G denotes A1 group. Okay, so using the group A1 or A1 tilde, we can recover the classical Puiseux block form. In fact, we can consider in the first element of the parameterization for all branch, except to the branch belong to the second block element in this way. Here denote the slope of the tangent line. And for the branch belong to the second block, we have a similar parameterization. It's very, very simple to obtain this. And it is important to say that using the topological information, for instance, the Symbolic ring gamma, and the Symbolic ring has a conductor, kappa, and the conductor in this situation is an element in the Symbolic ring, such kappa plus n natural numbers belong to the gamma, and kappa minus any element in the canonical basis doesn't belong to gamma. So using the conductor, this information of the Symbolic ring, this topological information, we can obtain a simpler representative in the analytic class. In fact, we can consider a representative given by a polynomial. We can truncate the power series, the parameterization. And the exponent di is related to the kappa in the following way. Di is kappa I plus 2 if you have just one branch and the multiplicity is less or equal to 2. The kappa is, the D is kappa plus 1 if we have just two blocks, two branches, and the multiplicity is equal to 1. This corresponds to the regular and transversal branches. And di is precisely the coordinate kappa I in another case. So we can truncate the parameterization, and this is nice because we can compute effectively. And in order to obtain now a normal form with respect the G group, G is A1 or E1 tilde, we consider a analytic invariant. And this invariant is obtained, consider a fraction ideal defined by one forms. So we consider omega A1, the set of one forms given by this way, where eta 2 and eta 1 belong to the maximal ideal square. And when we consider A1 tilde group, the omega is the one form given by this way, where eta 2 belong to the maximal ideal square, but the eta 1 belong to the ideal generated by x squared y. So consider this set of one forms according to the G. We get the following fraction ideal of the local ring associated to the curve. And this fraction idea is given by, we consider one form in the corresponding set. We consider the pullback of this form with respect with its parameterization, and we divide by the multiplicity, ti to the multiplicity. This is a fraction ideal of the local ring of the curve. And so we consider the natural valuation of CT, and we can compute the values. And in this way, we have the lambda G, the set of values of the elements in the fraction idea. The lambda G is a G invariant, A or A1 tilde invariant. And we can compute this set of invariant for a specifically mu germ, or if we fix a topological class given by a semi-ring, we can compute using an algorithm using standard base for fraction idea, all the possibility for this invariant in the fixed topological class. And fixing a topological class given by a same ring, there are only a finite many invariants lambda G. So using the lambda G, we have this proposition, and this proposition says we can remove some terms in the mood germ. Given a positive integer in a mood germ, if there exists a subset of indexes such that we obtain an element in the fraction ideal, e.g. in this way, with the coefficients bi are free for all index belong to L, then we obtain a mood germ equivalent to the previous one with the same k minus 1 jet, and we can remove the term t to the k for all irreducible component indexed by L. Okay, the aim is eliminate to the terms of order k from the maximum number of branches, prioritize the first elements in the mood germ. And we denote by Lk the element satisfying the star condition with this property. So we can compute the principal part of lambda G, and the principal part corresponds to the box with vertex determined by the orange in the conductor, and we can compute using not the fraction ideal, but the set lambda G, consider the properties from the elements in the diagonal. Here we have two examples of the principal part of lambda G. So in this way, we have two theorems to finish the talk. The first one, given the semi-ring and the set lambda G, we can obtain a normal form for the mood germ using just the set L present before, and such normal form are equivalent if only if they are equal. And using the homotety group to finish the talk, we can normalize, we can consider the action of the homotety group, and we can compare the parameterization. We can normalize, choosing the appropriate value to the alpha and gamma, and so on. We have obtained this theorem. And this theorem allows to put n mood germ in an appropriate form and compare the coefficient according to the homotety. So this allows to obtain the A normal form, and so we can obtain the analytic equivalence just to permutate the branch and compare the A normal form using the previous theorem. It's just to compute the previous invariant and compare using the previous theorem. Okay, well, I think that's all, and thank you very much for your attention.
Thank you.
Right.
All right, questions?
Okay.
Comments?
Have you ever tried to implement any of your results?
And to compute, for instance, the standard base for the fraction ideal to 1 and 2 and 3 irreducible components, yes, we have an algorithm to obtain this one. But for more than one is difficult because we have to compute, for instance, several steps and compute the change of coordinates. It is not so easy to obtain this one.
Mm-hmm. I see.
More questions, comments?
Okay. Good.
All right, thank you again.
Thank you. Thank you.